Hi, I am Ahmed Dawood, and in this session we will see multiple regression. So we started our module from the AI, ML, deep learning difference. Then we moved on what is actually the machine learning, some introduction of machine learning. Then we have started one of the algorithm of supervised machine learning, which was linear regression for the problems in which we have a target variable, continuous variable. Then we moved on how we can train our linear regressor model. We have seen two methods. One is direct method, one is gradient descent. Okay. Uh, and after these training algorithms, we moved on the how we can evaluate our regression model. There are some metrics that we have learned, like here mean absolute error, mean square error, RMSC, root mean square error. Then one of the famous and mostly use R squared, then moved on adjusted R squared. So till now we have seen the linear regression in which we are discussing just one independent variable. Like here we are seeing the equation which was like that mx plus c, in which there was just one independent variable. Okay, so why we are using, just for the sake of simplicity, or to build our concept on the how actually linear regression works. So if there will be, of course, in real world problems, there are not such a problem that have only one independent variable. There are multiple independent variables we have to tackle, and we have to train our model on that. Okay, if there are multiple independent variable, then we will. Some of you already know about that. If they know about the equation of line, so and I probably I also have discussed. So when we have multiple independent variable, we extend this equation. Okay, we extend this equation. So before going towards this, how we extend this equation, I want to elaborate here. So machine learning and deep learning. Okay, as I told you, deep learning is this, you can say, sub part of the or subclass of machine learning. In machine learning, when we have the equation of line like this, we usually call the terms intercept and coefficient. Okay, uh, but in the case of deep learning, we usually call the terms Bystrom and weights. Okay, so it is important to say you to elaborate these terms, because sometimes we are using the word, or we are when we are doing some discussions, we use the term weight or coefficient. Okay, so it's not a, you can say it's have no difference, you can use, it's up to you, but mostly we listen from people of deep learning, Bystrom and Wade, and the people that belong to machine learning usually use these terms intercept and coefficient. So in this session we will see the extension of linear regression, which will be the multiple regression. And after discussing this multiple regression, we will jump towards some practical code, and we will see how we can code this multiple regression. It's the same way like we did for the linear regression. Just you have to use the same class sklearn, this library, and we will import our linear regression from the sklearn, and we can use that linear regression. Okay. So before that, I will convert this equation y is equal to mx plus c. Y is equal theta 0 plus theta 1 x1. Okay, so and I also have told you that use different notations, it's not important, it's just you can see the variable names, so it's up to you, you can use any uh, notation here. Okay, here I am using theta 0 theta 1 x1, and it's the same, theta 0 is like an intercept and theta 1 is a coefficient. Okay. So, in the last sessions, we were discussing the example of area and price. Okay, so area was a independent variable, price was some of the you can say price was target variable or dependent variable. So if we extend our equation of which was this one, y cap theta 0 plus theta 1 x1, if we have just one variable like here we have area. If I will extend this equation, the equation will be like that: theta 1 x1, theta 2 x2, theta 3 x3, theta n xn. Okay. If we have n number of features, if we have n number of independent variables, then our theta will be uh, our thetas also will be n times. Okay, we have. So or in other words, you can say for each variable, for each independent variable, we have a coefficient in the equation, okay? And intercept will be remain 1 in the whole process. And why it remain 1? And you can see the nature of theta 0, which is actually intercept. If we have a model like this is a model, this is a model. So this model, when we have in multi-dimensional space, so this model, the direction of this model, like the angle of this model was presented by the coefficients, but intercept just elaborate or explain the intercept. Okay, how much we want to shift our model. Like if we shift our model upward, then it will be like this. Okay, if we have to move this model downward, down direction, it will be like this. Okay, so intercept just shift the model in the y-axis up or down. When we have to rotate our model, okay, in this at which angle our model should be, okay, then coefficients play a role. So that's why theta will, our intercept will be only one, and our coefficients will be as much number of times we have as number of independent variables we have. Okay, like if we have n independent variables, then our thetas will be also equal to 1. And we can also summarize this whole part, this whole equation in the sigma notation, in which sigma, our sigma, and here I will start from 0 to n, and I have started it from the 0 to n. In some books you will also see this type of notation, like I is equal to 0, and here theta 0 x 0, theta 0 x 0, then theta 1 x1, theta 2 x2, and this x1 x 0 we simply make it hard code that x 0 is equal to 1, always is equal to 1. So when you will multiply theta 0 with 1, it's the same, is equal to theta 0. Okay, so just I have changed the notation here. Now let's say how we have instead of one independent variable that we have here area, we have a data set like that, let's say, okay, in which we have in independent variables, we also have bedrooms follows. Okay, so there we have three independent variables. How we can write the equation for that? It's the simple, as we have three independent variables, so here will be, if I will use, okay, so one intercept theta 0, then theta 1 x1, theta 2 x2, theta 3 x3, as we have three independent variables like x1, here you can say present or donate floors, x2 here denote the bedrooms, and x3 here presenting area. Okay, so here theta 1, theta 2, theta 3, these are the coefficients for these three variables, independent variables, and there is just one intercept. Okay, if you will you want to see in more explanatory way, we can write in this way the equation. Predicted price, our predicted price will be theta 0 plus theta 1 into floors plus theta 2 into bedrooms plus theta 3 into areas. Now here you can see during our training phase we have to find this theta 0, theta 1, theta 2, theta 3, the values of these parameters, these four parameters we have to find, and what type of values we want to see, we want to find which has minimum SSE, okay, which has minimum SSE. We want these four parameter values where SSE is minimum. And in the same way, in the training phase, like our same formula we will use, like we were using the formula y minus y cap. Okay, now here our in multiple regression, as our y cap is updated because it has multiple independent variables, so in the same way we will update our updated y cap will be here. Okay, so this will be our updated y cap, theta 0 plus theta 1 x1 theta 2 x2 plus into theta m xm. So here I have just if I will show you in this way. Okay, so I just have here you can see, one second. Okay, here I have same use the equation some little bit different notations. Just I will elaborate you in this way. So we were having our usually we have our error function, or you can say loss function, cost function. Okay, we have like this I from starting from 1, and here we have y which is our true values, and here y predicted. Okay, so square I can write it this way. Okay, we have usually equation like that. What this I starting from 1 to n, so why this 1 to n, our n is representing here, and usually represent the number of samples we have in our data set. Okay, or you can say how many number of rows we have in our data set, how many number of rows we have in our data set. This is the n number of rows we have in data set. So here n is represent number of rows. Now here this x1 I write in this way. Maybe in some sources you will see some different notations here. I have used these notations so that you can make the clear difference between some variables. Like this x1 is not confused with this y I that in the subscript. Okay, so here x1 is the same, the feature 1, feature 2, feature n. Okay, if we have just three features, so here will be x1, x2 and x3. And here this I part is just denoting here the number of rows. Okay, I starting from 1 to n, so number of rows, the row 1, row 2, row 3, row 4, row 5, in this way. There will be x1, like this x1 I representing the rows in the x1. Let's say this one is x1, this is x2, x3, and this is our target variable. Okay, like in our case x1 here is mm, floors. Okay, so here the first value of x1 will be x. You can see the x1 will be here in the subscript, you have x1. In the same way, the second value of x1 will be x1 2, and in this way. Okay, so it's the same. There is no different, as just a different notations here. Okay, so m, if we have m number of independent variables. Okay, so here that's why this m. Okay, and n is number of samples. If I will write in this way, you will get a more clear idea. Like we have usually this equation that we have seen. Okay, usually in sources you will not see in the same way. Maybe, sorry, this will be, one second. Okay, this one starting from I1 to n. So here n is representing number of samples. Number of samples. Okay. Now we will write in the SSE, we are writing our function in terms of theta. Okay, theta is just the parameters. Like here that previously we have seen m and c, just we have two parameters just because of one independent variable. So till now we have seen the equation like that. Okay, m x I plus c. Okay, so this type of equation. Now we have equation like this, SSE theta. there will be multiple, if we have multiple independent variables, so our equation will be this way. This will be our true value. Here our predicted, if we have multiple predicted independent variables, then the equation will be in this way: theta 0 plus theta 1. Here I will write theta 1 x1 plus theta 2 x2 plus so on theta m xn. Okay, so here you can see for each variable, like here this is I, from 1 to n we have to use this one. So in the same way, because we have to see the difference of each sample, each row, in the each row what is the predicted value and what is our true value in each sample. Okay, each data point we will see. So that's why here I. Okay, so I hope I have used a lot of time here. So okay, the same as I told you, the same class we will use during our coding. For the library, we will use linear regression imported by from the scalar. Okay. So here one important concept I want to tell. It's also obvious. It should be clear to you. Like if we have one independent variable, like here we have one independent variable. Um, this okay. We have one independent variable area and one dependent variable. So then we can plot a two-dimensional graph here like this way. On like x-axis, there is area we have. On the y-axis, we can say we have a price. Okay, and our data set, you can say, which will be which has total two columns, one independent column and one is dependent column. So we are total two column in our data set. So our graph will be two dimensional. Okay, so our graph will be two dimensional and our model will be one dimensional here. Okay, you can say that our model is just a line, so it is one dimensional. Okay, and if we will see, if we have one independent variable, then our we will have one coefficient. Okay, one coefficient we will have and one intercept we will have. Okay, in the same way, we will grow our graph. Like if we have two independent variables and one dependent variable, of course. So there will be we will have total three variables in our data set. Okay, so our graph, if we will plot the graph, like on the x-axis there are number of bedrooms. On the you can say on the y-axis, if on the y-axis there is a area, and on the z-axis there is a price. Okay, so we have three-dimensional plot here, and our model will be uh, like a plane. Okay, model will be like a plane which will be a two-dimensional. Like in the case of when we have two-dimensional data set, then our model will be of one-dimensional. Okay, just a line. When we have three-dimensional data set, then we have our model like a plane which will be a two-dimensional. Okay, so why I am telling you this way? Because when we have more than three variables total, here in this data set we have just three variables. So if we have more than three variables in our data set, then we cannot plot our graph. Okay, we can not visualize actually in this real world we cannot visualize our plot, how we can plot a four dimensional in fourth dimensional space. So we can't do that. So that's why, for the sake of simplicity, till now we have used the just one variable and two variable. So in the real world problems, we have multiple variables and we cannot plot the graphs. So we have to estimate and we have to extend our equations, like we have extended from one variable to two variable. In the same way, we will extend the equation and our analysis in the same way from two variable to three, three to four, four to five. We cannot actually visualize the dimensions but we can do this mathematically. Okay, we cannot do by visually, we cannot plot some graph, but we can do this you can say mathematically. Okay, in this case, like we have three variables in which two independent variables. If two independent variables, then we will have two coefficients. Normally, we will have two coefficients and one intercept. Okay, intercept remain always one. Okay, when we will go in the part of neural network, intercept will remain one. Usually, we will increase our coefficient number of coefficients as our independent variables are growing. Okay, if our data will be more than will have more than three variables or have dimensions more than three, then we cannot draw the plot. So that's if I will show you how this two-dimensional plot looks like. If I will show you here, just to give you idea, like in this way, our plot two-dimensional model will be okay. It's just an example. Here you can see our data points will be in the three-dimensional space. If you are sitting in your room, then you can visualize if the data points in the room in the space of the room, then model will be like a plane. Okay, the linear model will be like a plane. In this way, you can say like this red line, red axis, you can say x-axis, this green one, y-axis, this blue one, z-axis. Then you can visualize how our plane looks like. Okay, how our model, like this orange one is our model, linear regressor. So here you can see, okay, this model will be the best fit model, or you can say best fit plane data is that is estimating the our predictions and have minimum error with the true data points. Okay, in this way our model will be when we have two independent variables and one dependent variable. Okay. So now we will see our code, how we can code our linear regressor. So before going towards the code, I want to just give you a review or a recap how testing and validating works and what's the reason behind that. Because in the code we will do some splitting of our data set. Okay, I hope I have explained you before that session. Usually we have a data set like this one. We have data set. Uh, okay, I will do in very more presented way. Okay, let's say we have this data set. Okay, in which we can say we have these are the our variables like we have floors, rooms, and area, and here we have our price. And then the same way, this was our data set. Okay, okay. So this data set we have. Now we have to train our model, and after training of model, we have to deploy this model into our production, into our site or into our application. Okay, so when we have a model and when we have to do some sort of here the purpose is the same, like in the case of this data set, our purpose is to predict the price when we have the floor, how many floor the house has, how many rooms the house has, how bigger the house in term of area, then we have to predict the price for that house. Okay, so uh, if we will train our model on the whole data set, then how we can evaluate that our model is good or bad. Okay, so for that purpose, we usually what we will do, we split our data set. Here if I will see, usually we split our data set in this way. Okay, split our data set and we use one part for a training. Okay, we consider that we just have this data set during our training. Okay, we consider that we have just this data set, and this data set we will not use, or we usually not use during our training phase. We keep it on the other side, and we consider that we have just this training data set. Okay, just this training data set. Like here I have, if I we have just this training data set. So we consider here we have separated our data set into two parts. One part is training part, or one data set is considered as a training data set, and the other data set we usually consider as a test data set. Okay. Oh, and we assume that the test data set is like a real world data points that will user use as an input in the future. Okay, but it is actually the data set that we have originally we have just we have gotten a part of that original data set here. Also in the test data set, like this is the test data set, so we have these independent variables, and we also have the true values of against these independent, or against these data points. Okay, against these data points we also have our true values. Now our model, after the training part, we will feed these data points to our model, and model will predict some values. Okay, then we will compare our model predictions, which will be like this, with our true values. Okay, for the sake of how good our model is. Okay, usually we do this in this way. And in some of the cases when we are doing our pre-processing part. Okay, in our pre-processing part, we do some transformation or scaling on our dataset for the sake of removing like skewness in our variables, or you can say to make the variables on the same scale. Okay, so in this like when we are doing our training, our yeah, when we are doing our training, we do scaling on this or transformation. You can say scaling or transformation we do usually before feeding our training data to our model. Okay, so when we will we have done with our training part, we have done our training, then during our when we have to testing our model, how good our model is, we have a test data set, and before feeding this test data set to the model to do some predictions, to get some prediction by the model, we do again scaling or transformation of our test data set into the same you can say into the same type of data set, or in the same type of data points that we have feed to our model. Okay, that we have fed our to our model during our training phase. We will try to feed the same data points with the same type of scaling, with the same, or if we are doing some other transformation, we have to uh, feed the same transformation before to get some prediction by the model. Okay, so we will also see these those stuff in our code. What is we will implement multiple regression. We will do some transformation on our variables, and I will elaborate there why we will we are doing the transformation, and the part of splitting our dataset into training and testing dataset. And okay, so moving on towards the part of uh, the code of multiple regression. Okay, so here we have this data set. This is data set of the automobiles, in which there are multiple variables. So here, this miles per gallon we will consider in this session as a target variable, and the other variables like cylinder, displacement, horsepower, weight, acceleration, model year, origin, car name. These are the can be considered as the independent variables. Okay.
So here in this dataset we have about 400 data points here. About 400 data points we will have here. And last time, if you can recall, we did in the we have used the a very small dataset just to elaborate what is actually linear regression. And because we have to do some calculations, or we have to run our algorithm theoretically. Okay, so that's why I have used very small data set of 5 points, and just one independent variable, which was area, and one dependent variable, which was price. Okay, so here in this that session we will see we will explore a data set, and we will use linear regression with multiple variables instead of just one independent variable. Okay, so multiple regression, you can say that when we have more than one independent variable, then we can say multiple regression. And it's how we can apply and how we can do code for that multiple regression. It's uh, exact same with the like we did in the case of linear regression just for one independent variable. Okay, so here first of all, I will import some important libraries like pandas, numpy, seaborn for visualization, and linear regression or class from the scikit-learn. Okay, that we will use here. Train test split, I will use here to split my original dataset into training data set and into testing dataset. Training dataset we will use during our training of model, which is linear regression, and test dataset we will use to test our model, how good the model we have. Okay, now linear regression is just a concept that we are using linear model. Okay, multiple regression is the same as linear regression. Okay, just we did last time, or in the last coding parts, or we have done the code, and in the last sessions we are just dealing with one independent variable. In this session we will deal with the you can say multiple independent variables. Okay, so the same module we will use. Okay, and I have shown you if you will extend the equation of y is equal mx plus c that we have converted into y is equal theta 0 plus theta 1 x1, we can extend this equation up to n number of features or independent variables. Here I am importing warnings to just ignore the warning. I am here doing filter warning ignore. I am reading my dataset auto mpg.csv file into data frame 1, and here we have multiple just mile per gallon as a target variable and multiple independent variables. Now here I will use just two independent variables. Okay, like and 400 total 400 data points we will have in our data set. Like here we just have used one variable, here I will use two variable. The reason is that why I am using just two independent variable, so that we can plot a graph in three-dimensional space. If we will use multiple, let's say we will use three independent variable, then total variables we will have four. And if we want to plot for dimensional graph or plot, we can't do that. Okay, that I have discussed in the theoretical part. Okay, I am just extracting three variables from here: horsepower, weight, and mile per gallon, and here I have given the name data frame 2, df2. So here df2, now it seems like this df2 has the numerical values in the horsepower, weight, mile per gallon, but actually it is that we are looking, but actually these are the numerical values, or these are can be a string behind that. Okay, so to explore that, before going towards the modeling part, I will check the type of by using info command. And here I have seen that the horsepower that we are uh, that seems like it's numerical, but here it is object variable. Okay, object data type, so can be numerical values. So to see that this object data type have what type of values in it. Okay, this dot object data type of this column horsepower. Okay, or you can say, okay, To explore that horsepower dot unique, I have run the command. Here I have seen these unique values in the horsepower column. Okay, so here yeah, all the values are in single code, so these values are not numerical values, these are actually strings. Okay, so we have to convert these values and this column into from like it is already in the object data type, so we will convert this into some integer data type. Okay, so before that, here you can see there is some noise also in that column. Okay, which is in the form of question mark. So I will also remove the rows that containing question marks. Okay, so here there are six data points or six samples or six rows in our data set which are actually having question marks in the horsepower column. Okay, so I am just ignoring that noise and just extracting the data set that is without the rows that containing question marks. Okay, now I have this data set data frame 3. Now in the data frame 3, the horsepower is of categorical type, or you can say or contain the values in this string format. So I will convert this horsepower column into integer format. Here I have converted that. Okay, so I have by converting it into integer by using as type command, then I have just uh, uh, cast back to towards the its main data frame original horsepower column. Okay, so here now I have run the any unique command to see how many unique values in my uh, this small data set have, in which there are just two independent variables, horsepower and weight, and one dependent variable. So there are multiple unique values because just the reason is it's a continuous column. So that's why. So first of all, I will run the command correlation command data frame 3 dot COR. So by running this command, you have seen from here, when we will see the correlation with the horsepower and mile per gallon, you can see it's a negative. Weight also has a negative correlation with the mile per gallon. And the strength, the horsepower has a strength of 0.77 and the weight has 0.83. Okay, both have enough uh, good strengths with the target variable, and they have negative correlated with the target variable. Now by using pair plot, we will see how these are. Okay, in the last say, when the horsepower is on the x-axis and on the y-axis the mile per gallon, here you can see like data points are showing in this way that they are decreasing with the or you can say miles per gallon decreasing with the increase of horsepower. Okay, so they are negative correlated, and the strength you have seen 0.77. In the case of weight on the x-axis and mile per gallon on the y-axis, again the correlation is negative as weight is increasing, miles per gallon is decreasing. Okay, so if we will see the distribution of horsepower weight, so horsepower has distribution here. This is the histogram of horsepower. Okay, so it seems like the data is in the horsepower column is right skewed. Okay, and in the case of weight, again the data set or the values in the weight column are also right skewed. Seems to be right skewed. Okay, so first of all, I will split my data set into independent columns. I will make the name X, and the dependent column I will give the name Y. So here X will contain the independent variables. So in our case, these are just two, horsepower and weight, and dependent column here the miles per gallon, and the name is Y. Okay, now we have X, Y. So here I am splitting my data set into a training data set and testing data set. Okay. So training dataset we will use in the training phase of the model, and testing dataset we will use in the testing phase of the model. So here I am using the train test function that we have imported from the scikit-learn. X, Y, that X is a independent variables, Y is dependent variable. Test size here I have given is 0.3. It means 30% of the data points. Like we have 400 data points total, and out of 400 there are 30 percent data points I am saying that should be considered as a test data points, okay? Like about 130 data points should be considered as. If we will see here, yeah, 118 rows will be considered as a test data points, and 274 rows should be considered as a training data points. So here I have given in the form of percentage, or you can say ratio 0.3%. I want my test data set size. Random state here I have mentioned is equal to 1. Okay, so it's up to you what you want to do. Here you can mention any number here, random state. Okay, it is just a random state because it is randomly select the uh, data points from the original data set. Okay, it's not the same like always. It will separate the upper part as a training part, the lower part as a test one. To make the generalized data sets both, split the data sets randomly. Okay, so here I have four data sets total. Xtrain, which is independent variables for the training training data set. Okay, here you can say independent variables in the test data set. These are this is dependent variable we will use during training data set, and this is again dependent or target variable data points that we will use during our testing phase. Okay, so here I am just using xtrain.copy. I am creating a copy and given the name underscore two. It's just a purpose to if we will use it later. Okay, I am make it in this way. Okay, so here xtrain have these two columns. Okay, independent variables and about 274 data points in that. So in the same way, if you want to see Y-train, Y-train also will have same number of data points and just one target column. Okay, here you can see 274 rows and one column. X-test has 118 rows and two independent variables, and in the same way, Y-test will have 118 rows and just one target column. Okay. So first of all, normalization I will do on that. Why I'm doing normalization? You have seen during the pair plot here, my independent variables seems to be right skewed. Okay, right skewed, and linear regression by nature it's sensitive to outliers. Okay, we should feed the normalized data to our model to make the model generalize. Okay, if we have extreme values in our data that we are or in our variables that we are feeding to our model, then there is no chance that our model will be get biased, okay, by the extreme values or by the outliers. So first I am just normalizing my variable values so that we can feed normalized data to our model. So that's why here I am doing transformation, or you can say normalization I want to do here. So for that purpose I am using power transformer. Power transformer I am importing from scikit-learn pre-processing module, and I have done this part. I hope power transformer in the fundamentals of AI/ML. I have not done this power transformer by theoretical way. What the nature behind that, how it's underlying concept here, but we have done it practical. We have used this module. Okay. So this module is very good in the case of if we want to make our variable or we want to remove skewness from our data. Okay. So here I am using this power transformer, and here I am going to fit my training data. Okay. So here I am fitting my independent training data. We no need to do on the transformation of the dependent variable, because we want such a model that is explain the variation in the target column by using independent variables. Okay, so we don't need to do transformation on the dependent column. Okay, so we will do the transformation on the independent variables, and here I am going to fit module. During fit
module, it's in the model, when we are using some model, then we usually call during fit module we are doing training of the model, okay. But here in the case of transformer, you can say that during the fit module it's calculating its parameters, okay, parameter values, like when we are using the standard scalar, okay. So during the fit part of standard scalar actually calculating the mean and standard deviation of the variable. Okay, in this way, power transformer also during fit function will calculate the its parameter values. By using the parameter values that it has calculated, it will convert the variable in the transform function. Okay, so in the this PT to transform, I am transforming my train independent variables, and again I am passing back to the same variable x train. Okay. So here you can say I am making change in the xtrain, transforming my xtrain variable, and again passing towards back to the xtrain. Okay. So now I have okay, I have here transformed independent variables in my this training data set. Okay. So the same transformation that we have done here, pt dot power transformer dot fit, the same parameter values that it has calculated here in the case of training data set, we will use the same power transformer for the case of uh, when we have to do some prediction by our model or to calculate the score of the model. We will do the same transformation on the testing data set. Okay. So I have also explained you theoretically that why the reason is that the same transformation like we did on the training part. Why we use the same? Because in testing data points, we have considered as a real world data points. Okay. Till now, we have considered that we have just these data points that we have in the X-train, the training data set. And in the real world scenario, there can be a chance that any type of data points there will become, okay. Always there will not like a millions of data points in this way in the form of data, like in the form of data sets, their results cannot come to uh, towards our application, or that's why you can say the reason is that we are converting our test data points into the same transformation that we did on our training data set before feeding to other model. Okay. So we will use the same transformation on the test data points, okay, individually, when so that when our model will be deployed on some application, so we will again before the model we will do some transformation of any data points entered by the user. Okay. So any data point entered by the user, then in the application first the pre-process the data, or you can say transform data point, then the transform data point will be fed to the model to get prediction, then model will give the result to the user. Okay. In the real world scenario, so that's why as we have simulate our testing data set as a real world data points, so that's why we will do the same transformation that we did in the training part. Okay. Okay, we now have linear regression model. Here I am creating instance of linear regression, multiple linear regression regressor. Here I am doing the training of my linear regressor, multiple linear regressor dot fit xtrain, which is transformed training independent variables, and this is our target column. Okay. So I am feeding my training data set to train my model. Uh, I have told you fit function is to train the model, which you can say to calculate the parameter values. Here I have trained that. So before that we have seen DF3 dot correlation. So here in that part of multiple linear. Okay. So here we have a multiple linear regressor that we have trained here in by using training data set. So the coefficient values and the intercept of the model that we have done with the training. Okay. So here
we have the values minus 2.82, coefficient 1, you can say theta 1. This is minus 3.9, which will be theta 2. That theta 0 is 23.41 here. Okay. So from the this you can also analyze, like we have a negative correlation, so that's why here the coefficient values are also negative. And from the strength, you can also see here the weight. In the correlation, weight is presenting like it have 83% relation with the miles per gallon, while horsepower has 77. In the same way, you can see here 2.8 horsepower has strength, and the weight has 3.9. You can see that the linear relation of weight with miles per gallon is greater than the as compared to horsepower with the miles per gallon. Okay, you can see from here the correlation, uh, which has the high correlation with the target variable, which variable have high correlation with the target variable will have high linear relation with the target variable. Okay, mostly in the data analysis, or you can say statistical modeling, the linear regression also can be used as a part of uh, you can say as a part of analysis. Okay, and if we want to do some analysis, or to want to see the relation between multiple variables at a one time, so we can use linear regression for that purpose also. And I have also shown you in the part of visualization of fundamentals of AML how we can use linear regression to, and in the by using S C1 module, to see the linear relation between the variables. So here we have, during the training part, it has calculated these coefficients and intercept. And when the coefficients and intercept, or you can say the parameter values are calculated, then you can say you are done with your training part. Now here, the equation is y cap is equal theta 0 plus theta 1 x1 plus theta 2 x2. Okay, when you will now you will put the value of x1 and x2, any value of x1 and x2, you will get some prediction. Okay, if I will show you here. Here you can see we have, during our training part, we have calculated our coefficients and intercept. Okay, like this is theta 1, theta 2, and this is theta 0. Okay, theta 0 23.41, theta 1 minus 2.83, theta 2 minus 3.9. Now your equation is y cap, which is theta 0 plus theta 1 x1 theta 2. Okay, or you can say you are using here, if I will add it this way, predicted miles per gallon will be in this way: theta 0 plus theta 1 into x1 will be horsepower. Okay, plus theta 2 into weight of automobile. Okay, now you will pass any value here, like this is 23.41, this is here minus 2.83, and this is here minus 3.9. Okay, now you have to just pass the horsepower value, horsepower and weight, any value of horsepower and weight, you will get some predicted value of mile per gallon. Okay, so you can say during that training part, you have calculated the parameter values here. Okay, now you can say you are done with the training. Now to calculate the score, what score here the model have. So here I'm using the score function of linear regression provided by the linear regression class of scikit-learn. So we have seen the score in the R square method. Like this is, you can say we are here calculating the R square score of the model. So here I am passing testing data set. Okay, so testing independent variables. So before passing the independent variable, I am just transforming independent variable by using the same transformer that we have fitted on the training data set. Okay, same transformer I am using here, and this is testing data point, testing true values. Okay, so how the score works, I told you last time also, that it calculate the predicted values of this data set. Okay, independent variables by using these independent variables, and then the predicted values it will compare with this y-test with the true values, and then it will calculate the score. Okay, by using the same formula of r square. Okay, 0.76, or you can say 76% the accuracy of our model is, or you can say 76% variation of miles per gallon is explained by our model, or you can say 76% variation in the target column is explained by your independent variables that you have horsepower and weight. Okay, if you want to do some prediction, you can use the predict class, and you can print the predictions. Okay, so here I am using I am want to see the predictions for all the testing data points. So these are the predictions. Okay, so now you can compare these prediction with your true values. Okay, so I am going to flat this prediction so that here mm, I will go towards the plotting of the variables, and I am interested in to see the what type of model I have achieved here. So it's the predictions are in the two-dimensional array. So here you can see it's these were on the two-dimensional array. So I am just converting this into one-dimensional array. So here we will plot some graphs. Okay. The purpose of using just two independent variables was also the same, that we can plot the three-dimensional space. Okay. So here matplotlib I am using here to do some three-dimensional graphs. Here you can say figure is equal to plot dot figure function, and to see the three-dimensional axis I am using a plot dot axis projection 3D. Okay. Here the projection is 3D. So same 3D projection, and here I am using scatter 3D function of matplotlib, and here I am passing three variables. Okay, first x, y, z. Okay, color is blue. So this is scatter points in the three, like this is x from 50 and 200 towards 200. This is x, which is horsepower on the x-axis from 2000 to 5000 side. This side is y-axis, you can consider, like this is weight, and miles per gallon is on in this direction of z from 10 to 40. Okay, so these are scatter points in the three-dimensional space. You can see if you are sitting in room, you can say that these are the data points in the three-dimensional space in the air of the room, you can say. If you there are a lot of this data I have plotted the for the whole 400 data points. Okay, if you will plot the graph for just testing data sets, you can see there will be 118 data points here. Okay, so now when we will plot our graph, okay, so predictions, plot 3D function I will use here. Now you can see here very irregular red line I am saying here. It is the reason that I am using here matplotlib. So in the seaborn, we can use line plot in the two-dimensional space. It will generate the line by itself. But here, uh, it has calculated the line matplotlib in some different way. Okay, like if it has there is some points is not in order in our data set, then it will see give you a irregular line. Okay, to see the some regular line, I will just alter my dataset that I have this dataset. I have testing dataset that I want to visualize the model on the testing dataset. Okay, so I will sort the dataset with respect to horsepower. Okay, so I have created another dataset, dataset underscore predictions, which has horsepower and weight. I have added the mile per gallon true values here,
and predicted underscore mile per gallon predicted values in that data set. Now I will sort this data set with respect to horsepower. Now all the values are sorted in the way like horsepower uh, is in the increasing order. Okay, so all the data points accordingly. So now you can see there is some regular model as compared to this one. Okay, this is the customization of Matplotlib. That's why I recommended you the Seaborn library, which done a lot of stuff for you by itself. Okay, so here this line is our model that we have achieved. Now, maybe you get confused that this is a line and I have shown you the plane. Okay, so it's also the customization of Matplotlib. Maybe some module available of Matplotlib that can give you a plane. Okay, but actually this is a plane. Okay, due to Matplotlib plot 3D function, I am getting here just a line, but this is a plane actually. Okay, so if some of you can explore the matplotlib, if there will be any function of matplotlib that can plot the plane, then you can try it by yourself. Okay. Anyway, I will show you this model on the some other calculator, 3D calculator. Okay. So before going to towards that, I will show you 3D calculator. Okay, here this model I have plotted here the same equation that we have seen here minus 2.83 into horsepower plus 3 point, minus 3 minus 3.9 into weight plus 23.41. I have used the same equation here. Okay, and I have gotten this plot here in that three-dimensional place. You can see that your model is like that. Okay, this red is x-axis, green is y-axis, and this blue is z-axis. You can see this red line horsepower. Okay, on this axis z, on the z-axis there are weights, and on the blue axis you can say your miles per gallon. And in the three dimensional you have some data points, and this is your model. Okay, actually the model is like that. So here in the code, like it is showing this matplotlib is showing you a line because we have used the plot 3D. Okay, maybe some another function that can give you a plane, but here the aim is to give you concept. If you are interested, you can explore the matplotlib. Okay, matplotlib is very customized. So here when if we want to see the horsepower versus miles per gallon, like this is horsepower on the x-axis, miles per gallon. It is same as horsepower. This is red one. Okay, if you want to see the, yeah, in this way horsepower versus miles per gallon. Okay, your graph will be in this way. Okay, this way. Okay, if you are interested to see in this way your graph, you can see from here. Okay, it is in the line is very fluctuating. It is like it is the plane which is we have compressed the two-dimensional plane into just one line. So that's why it is giving you a line. It is not a, you can say that it is non-linear line. So it is a linear plane. Okay, that we have achieved here. And how you can prove that? You can prove by your equation that you have. Okay, by this equation you can prove that you have linear plane. There is no x square values here. Okay, you have x1 x2. Okay, there is no value which is x square, so that's why you can say you have linear plane, your model is linear. Okay, but it's due to multiple variables, we have two independent variables, so that's why it is not just a line, it's a plane. Okay, if you want to see weight versus miles per gallon, you can see. Okay, again it's also you can consider that like these green are weights. So in this way you can see this one will be can be like that. Okay, okay, maybe this plot is giving you some different visualization. Okay, so it's a very simple in here
this graph calculator is showing, but actually when you have done by the code by using this symbol, you are getting this type of line. Okay, so again, this is two-dimensional plane we have compressed into just one line, so that's here. But again, this is not non-linear line. Okay, this is plane that we are seeing in the two-dimensional space. Okay, that's why it is seems to be a line when you will see from the this line in the three-dimensional space, it will be a plane. Okay, so it's not a non-linear line. Okay, now here horsepower versus weight. I have plotted here a horsepower versus weight graph, and this is like this line. Okay, you can see that your data points are in this way. Okay, horsepower versus weight when you have independent your independent variables have data points in this way. Now if you lift this graph, okay, this line into z-axis, okay, into z-axis, like here if you have a z-axis and the z-axis will be miles per gallon, if you will lift this line upward, then you will get a plane. Okay, so actually your model is a plane, and I have told you in the theoretical part also, when you have three-dimensional data set, you will have a model of two dimension. Okay, when you have two coefficients, one intercept. Okay, in the same way, if your data set is growing, like your data is have 10 columns, total 10 columns, 9 column are independent and one column is dependent, then your uh, model will be nine dimensional. The reason is that you are having a variable, you are having your equation like that. If I will show you here, you will, if you have 10, okay, 10 uh, dimensional data set, it means that you have nine independent variables and one, of course, dependent variable. Okay, now your equation of model will be like that, from theta 0 plus theta 1 x1 theta 2 x2. Okay, you can write in this way, x1 x2 plus up to theta 9 x9. Okay, as nine variables are involved in your model's equation, so that's why your model will be a multi-dimensional. Your model will be, you can say, nine dimensional. So here in the real world, I told you multiple times, we cannot see the graph or plot uh, which is greater than three-dimensional. Okay, so we cannot see the four-dimensional space. So, but we can prove or calculate by mathematically. Like here, this is the equation we can prove. Like if the equation involved just one variable, like the equation like this, which has just one variable, then we can say this is the equation of line. When we involved with the two variable theta 1 x1 plus theta 2 x2, we can say that there are two variables involved here, then it will be the equation of plane. Okay, in this way we can prove mathematically that how many dimensions our model have, but we can't see. Okay, okay, so here you have seen that the same purpose, the same uh, linear regression we can use to uh, code the multiple regression, multiple variables, and I hope you already know that. But here, just to give you a recap and some different measures and some different type of visualization, how we can visualize, uh, I want to give you here, and you can say it's a type of like a, if there are some points that we need to consider, like in the linear regressor is very sensitive to outliers, so that's why we have used the power transformer to make the independent variables normalize. In the same way, you have learned in this session the train test split. Okay, training data point for the training phase, test data points to test the model. Okay, we have seen multiple other aspects and other concepts, you can say. So multiple regression is just where the multiple independent variables are involved, and it's a same linear regression. Okay, so linear regression, from the linear, keep in mind that here we are following the linearity, okay, no, not non-linearity, okay, because some models, like in the future, in the coming sessions, we will see non-linear models also. So till now we have done linear models, okay, linear regression. So I hope you got enough for today. So for now, thank you.